All right, we're going to start off with the basic review of forces, and hopefully this content is review for most of you, and if it is review, that's awesome. Feel free to skip this one or just watch it at double speed, but remember the goal here is to start from square one and then just build up, going through everything. That way, the goal is that if people are behind or they're kind of shaky on some of these concepts, we can hopefully get everyone up to speed so we're all on the same page. So anyways, a force. In kinesiology, we can think of a force as the push or the pull of one object on another object. I know that Molly already talked with you guys about this, and this slide is from her presentation. But as you can see here, when you apply a force to an object, you can have a few different effects. So the force can cause translation, which is basically just moving an object in a straight line. It can cause rotation, so moving an object in kind of a circular pattern around an axis of rotation, or a force can cause something to deform. So the object might not move, but you just kind of deform it and change the shape of the object. I think the easiest one for people to grasp is translation. So for example, here I have my backpack sitting on a table, and if I push on it or apply a force to it, the backpack's going to move, and it's just sliding in a straight line. So in this case, it's moving in a straight line, so it's just translation. On the other hand, if we have a door, for our example, this door moves, right? We can open it, we can close it, but this door cannot move in a straight line, and that's because there's these hinges on the door here, and these hinges kind of hold this end of the door in place. So when we push on the door, it can't move in a straight line. Instead, it has to rotate around those hinges. So again, because these hinges kind of hold everything in place here on this side of the door, it can't translate. Instead, it has to rotate. For the last example, for deforming an object, we can just use this pillow here. So this pillow on the table, I can push down on it, I can apply force here, and the pillow is not really moving, right? It's not sliding and it's not rotating, but I'm still deforming the object, or just kind of changing the shape of it by applying a force to it. Last thing to note with forces. In all these examples, when I applied force to something, it caused some type of movement, whether that was translation, rotation, or just deformation. Keep in mind that there are scenarios where you're applying forces to something, but you're not actually seeing any movement. So for example, if I'm just pushing against a brick wall, I'm applying force to it, but the wall is not actually moving, and you can't observe any movement going on there, even though there are forces involved. And we'll get into more concrete examples of this in just a little bit. But to summarize, in kinesiology, we can think of a force as the push or pull of one object on another. Moving on to moment arms. The moment arm is the perpendicular distance between the axis of rotation and the line of force. Just to clarify here, some people will refer to the axis of rotation as the fulcrum, and some people will refer to the line of force as the line of action. But these things, they mean the same thing, they're just different ways to refer to the same concept. One thing to note that people always forget about is that moment arm is a distance. The moment arm is not a force. The moment arm is the distance between the axis of rotation and the line of force. So going deeper into each of those terms, the axis of rotation is pretty straightforward. It's just the point that an object rotates around. So in the door example that we used earlier, the axis of rotation is the hinge on the door, since the rest of the door rotates around those hinges. In the example of the elbow joint here, this picture on the left, this little black dot, this elbow joint, is the axis of rotation because if I'm moving the elbow, this forearm kind of rotates around the elbow joint. So in this case, the elbow joint is the axis of rotation. Last thing with regard to axis of rotation, keep in mind that an axis of rotation is not always present, right? So with the door example, we have an axis, it's the hinge. With the elbow example, the axis is the elbow joint because things rotate around that joint. But with other things, like the backpack example, there is no axis of rotation. So remember, when I push on that backpack, there's nothing that the backpack was rotating around. It's just sliding in a straight line or translating. So just important to keep in mind, there's not always going to be an axis of rotation. So the second component of the moment arm is the line of force, or the line of action. So recall from Molly's lecture that all forces have two components. all forces have a magnitude and a direction. So the magnitude is like the strength or the size of the force, whereas the direction is just the direction in which the force is being applied. So if you look at this picture over here, the magnitude is just going to be represented by the length of the arrow. So the longer the arrow is, the greater the magnitude. And then the direction is pretty straightforward. It's just the direction that the force is pointing in. So the line of force is just an imaginary line which runs in the same direction as the force vector. So don't overcomplicate this, right? It should be pretty intuitive. In this picture here, right, there's this force vector is this solid black arrow which is pointing straight down because it's representing the force of gravity, and then the line of action is just this dashed line that runs like through the force vector and then kind of continues on infinitely. So again, line of action, just a line that kind of runs along the force vector. That's all it is. Now, we know what the center of rotation is, and we know what the force or the line of force is. So now we can easily find the moment arm, because the moment arm is just the distance between the line of force and the center of rotation. So again, at this picture right here, if we use this picture on the left, this line here, or this arrow, represents the force that's acting on the arm and just kind of pulling the arm down due to gravity. So in this case, the force is pointing straight down because gravity pulls you straight down, and then the center of rotation is still going to be this elbow joint over here. So in this example, the moment arm is just going to be this long red line. It's distance between the line of action and the axis of rotation. That's all it is. Super straightforward. In this example over here, same thing. Here's your force, here's your line of action, and here's the axis of rotation. So again, the moment arm is just this red line between the line of force and the center of rotation. Last slide focusing on moment arms, I promise. This picture here is from page 16 of your Newman textbook, and just to orient you, with this picture here, we're looking at a door, but we're looking down at the door from above. So this is top view looking down at a door. So here's the handle on the door that you turn and push, and then here's the hinge on the door, or the axis of rotation. So in this case, Newman's showing us 4 different ways to apply force. Here's force C right here. Here's force D. Oh, sorry, you can't see that. Here's force C. Here's force D. Here's force E over here, and then here's force F. So if you look at forces C and forces E, both of those forces have moment arms. And what that means is that there's a distance between the line of force and the center of rotation. So with C here, you can see that the force is applied way out at the door handle, and then it's applied in a direction that's kind of diagonal to the door. So here's the line of force right here, and then here's the center of rotation. So there's a distance between the axis of rotation and the line of force. So that's this black line right here. So since there is a distance there, that's our moment arm. For force E right here, same idea, right? Again, the force is applied at the door handle, kind of just pushing straight into the door. And so here's our direction of force, and here's our center of rotation. So the moment arm is this black line. It's the distance between the line of force and the center of rotation. Now, with force D, we have a force that's applied to the door handle over here. But in this case, if you look at the direction of the force goes straight through the door handle, and then it passes through the hinge of the door over here. So in this case, we don't actually have a moment arm because this line of force passes through the center of rotation. So there's no distance between the line of force and the center of rotation. That distance is 0, so our moment arm is essentially 0. Similar idea with force F over here. So force F, in this case, we're applying force directly to the hinges. And in this case, again, because that line of force has to pass directly through the hinge, there's no distance between that line of force and the center of rotation. So since that distance is 0, our moment arm is 0. Hopefully this turns out okay. I'm going to try to illustrate on this door here real quick. So if I push on this door handle here, then it's going to swing open, right? Easy, pretty obvious, right? It just moves. Whereas if I push on the door handle here and I just push straight that way toward the hinge, I can push on it as hard as I want, but it's not going to move. It's just kind of compressing the door in there against the hinges, and it's not actually going to rotate. Same deal if I come over here and instead of pressing on the door, I just press on the hinge itself. I can push on that hinge, but it's not actually going to rotate because there's no distance between the line of force and the axis of rotation. The last topic for this video is going to be torques, and torques are also called moments. So the definition of torque is just a tendency of a force to cause an object to rotate around an axis. And it's tough for me to give a strict, concrete definition of torque because it's kind of an abstract principle. So torque is not the same thing as force, but torque is created, or torque is present in response to a force when that force is causing something to rotate around an axis. Hopefully these examples help to make sense for you. If they don't help, I would go and talk to Marcy because she might be able to explain it better than I can. So one important thing to keep in mind is that a torque is the same thing as a moment. However, these are different than a moment arm. So remember, a moment arm is a distance, specifically, it's this yellow arrow here, it's the distance between the line of force and the axis of rotation. On the other hand, torque and moments, they do not refer to a distance. They kind of cause an object to rotate around its axis. So know these terms. People get these mixed up all the time, but you really want to know them and learn them now so you don't get confused later. So the formula for torque, which you should have learned, is just that torque is equal to the force multiplied by the moment arm. And to be clear, when we talk about force here, we're talking about the magnitude of the force. So just how big or how strong the force is, and that's going to be expressed in newtons. So if we look at this example here on the right, I mean, we don't have any numbers to put here, but here's the magnitude of the force, right? It's just represented by the length of the arrow. And then here's the moment arm. So if you wanted to calculate the torque or the moment, you would just multiply the force by the moment arm, and then that would give you your torque. Last thing to note for this slide is that because torque equals the force times the moment arm, if there is no moment arm, then you're not going to have any torque. So this picture here is from the last slide. It's the picture of when we're pushing on the door handle, but we're pushing in a direction so that the line of force goes straight through the hinges of the door. So in this case, the line of force is passing through the axis of rotation, therefore you don't have a moment arm. The moment arm equals 0. So in this case, the torque also equals 0, since the torque is the force multiplied by the moment arm. So if the torque equals 0, that means that you can push on the object, but that pushing or that force, it's not going to actually cause the object to rotate because there's no moment arm and therefore there's no torque. Using another example to illustrate that point, for this example, we're just going to use a seated knee extension where someone's sitting on a chair and then they just kick their leg out in front of them by straightening the knee. So when their knee is fully extended out in front of them, shown by this dashed line here, you can see that gravity is pulling down on the leg, and the point at which gravity is acting is way out here in front of the knee joint, right? So here's the force vector from gravity, just pulling down on the weight of the leg, and here's the line of force here, and then here's the moment arm, right? So you can see there's a big moment arm between the line of force and the actual knee joint. So because there's a big external moment arm, that means there's going to be a big external torque where gravity is really trying to cause rotation at that knee joint and pull the knee back into flexion. On the other hand, when the knee is already in 90 degrees of flexion, as shown here, gravity is still pulling down on the leg, right? And that's shown by this red arrow right here. So in this case, gravity is still pulling down on the leg, but if we look at the line of force here, the line of force passes directly through the knee joint. So in this case, there's no moment arm because there's no distance between the line of force and the axis of rotation, because the line of force goes through the axis of rotation. So because of this, there's no torque from gravity. So gravity's not actually trying to rotate the leg at all. It's pulling down on the leg, but it's not actually trying to cause any rotation at that knee joint. And this should be fairly intuitive, because if you sit on the side of a plinth and let your legs dangle, when your legs are just hanging there, when they're hanging straight down, your quadriceps, they don't need to be on. They can be relaxed, and your legs aren't going to go anywhere. They just kind of dangle. Whereas if you kick your knee out and you kick your legs out and your knees straighten, then your quadricep muscles have to work to keep that position, because gravity is trying to pull you back into knee flexion, and your muscles need to fight that. So just to summarize this slide, when looking at the effects of gravity when it's trying to move the body, if the line of force for gravity passes straight through the joint, then there's no moment arm, and that means that there's no moment, or there's no torque. And when that's the case, that means that gravity, even though it's pulling on that part of the body, it's not actually trying to cause any rotation there. So it's not trying to cause movement at that joint, and you can just kind of let the limb dangle. In kinesiology, we're going to have two main types of moments. We're going to have external moments and internal moments. External moments are caused by external forces acting on the body. Examples of these include the gravity or the weight of your limb, an actual weight like a barbell or a dumbbell, elastic bands. It could be like a cable machine, or it could just be another person pushing on you and applying a moment. For internal moments, those are caused by forces within the body acting on a joint. And these are primarily going to be caused by muscle and by tendon, since muscle pulls on tendon to move bone. Internal moments can also be caused by ligaments and other structures, but really, when we talk about internal moments, most of the time we're going to be focusing on muscle. All right, switching gears a bit, we're going to talk about types of muscle contractions. And this is something that most of you probably learned in undergrad, and it's something where you can probably give me the definitions, right? Like most of you can probably tell me what a concentric contraction is. But I'm going over this because a lot of people in my class, they can give you the definitions of these things, but then when it comes to actually applying them during different exercises, a lot of people really struggle. So hopefully this will help you to struggle a little bit less, and this slide and the next two slides on contraction types can hopefully serve as a bit of a cheat sheet where it should allow you to figure out what's going on during most exercises. So with that being said, muscle is always going to be in one of two states. It can either be on or it can be off. Some synonyms that you might hear: when a muscle is on, people can say that it's contracting, or it's firing, it's active, or it's activated. And when it's off, people might say that it's relaxed or it's passive. Basically, when it's off, it's not really doing anything. It's just kind of sitting there. Now, when a muscle's on, it's doing one of three things. And these are your three contraction types. You have concentric contractions, eccentric contractions, and isometric contractions. Again, I think most of you could tell me the definitions of these things, where with a concentric contraction, it's on and shortening. With an eccentric contraction, it's on and lengthening. And with an isometric contraction, it's on and the length's not changing. There's more details here on the slide, and you can read over these and make sure you understand it. I'm not going to go over it right now, and I'm going to save those details for a little bit later. But again, hopefully this slide can be a nice cheat sheet for you as we go on. As we discussed, a muscle can be on or it can be off. And when it's off, there's also three things that I can be doing. So when it's off, it can be relaxed and lengthening, it can be relaxed and shortening, or it can be relaxed with the length not actually changing. An important thing to note here is that when a muscle is relaxed, it's not causing motion, it's not controlling motion, and it's not preventing any motion. It's just off. It's not really doing anything that we care about, but its length still, sometimes the length still can be changing depending on what's going on. An exception to this rule is passive stiffness, which you might have discussed with Gretchen with your muscle elasticity, but we're not going to worry about that right now. We'll save that for later. Last set of rule here for contraction types. This will hopefully help you to determine whether there's an eccentric contraction occurring or a concentric contraction occurring. And again, this is something that people in my class struggled with, so hold on to this slide if you find it confusing, and hopefully this can serve as a nice cheat sheet. So this applies to all exercises where the resistance is coming from gravity. So it doesn't apply to exercises where you're using like an elastic band or where someone's pushing on you to cause motion. It only applies to basic gravity resisted exercises. So that could be anything with just body weight, or where you're lifting a barbell or a dumbbell and gravity is just pulling it straight down toward the ground. So with those sorts of exercises, when the weight or the limb is moving up, that means that muscle is causing the motion and it's a concentric contraction. So for example, during a bicep curl, when the weight is moving up, that means that it's concentric contraction and muscle is causing the motion. Now, when the weight or the limb is moving down, that means that gravity is causing the motion. And in this case, muscle is just controlling the motion and it's an eccentric contraction. And here's what I mean by controlling. If I'm here and then I just relax everything, my arm's just going to flop into extension, right? If I contract the biceps some and do an eccentric contraction, now it's controlling the motion, so it's a nice, slow, smooth, controlled motion. So again, if I just relax, if I just turn this muscle off, my arm is going to flop. But if I do an eccentric contraction with the biceps, then I'm just going to have a nice, slow extension, again, with gravity causing that motion. And the last one I think is pretty obvious. If the weight or the limb is just not moving and I'm holding it still like this, then gravity is trying to pull my elbow into extension, but my biceps are preventing that motion. So in this case, the muscle is performing an isometric contraction where there's just no motion and no change in length. Okay, this is actually the last set of rules. I promise we're almost done with these slides. The previous slide allowed us to figure out which type of contraction was occurring, so whether it's concentric, eccentric, isometric. This slide is going to tell us which muscle group is actually contracting the whole time and which muscle groups can be relaxed. So step one for this process is to ask yourself, during this exercise, what would happen if I just completely relaxed? So using the bicep curl as an example, if I'm performing bicep curls and then I just totally relax, then gravity is going to pull my elbow into extension, right? So if I relax, gravity pulls my elbow into extension. Step two is super simple. All we do with step two, we know that the active muscles are the muscles that perform the exact opposite motion. So in this case, if when I relax, gravity pulls me into elbow extension, the active muscles are going to be the muscles that cause elbow flexion, so the biceps or the elbow flexors. Keep in mind, these elbow flexors, they're going to be on the entire time, so they're going to be on during the concentric and during the eccentric. On the other hand, the antagonistic muscle group, in this case the triceps or the elbow extensors, they can actually be relaxed the entire time. So they're not contracting concentrically, they're not contracting eccentrically, they're just relaxed the entire time. And if you think about it, this should make sense, because the action of the triceps is to extend the elbow like this, but we don't need them to be on because gravity is already trying to pull us into elbow extension. So it would be a waste to have both gravity and the triceps trying to pull us into elbow extension.